Clinker Factor, the cement industry podcast.
Welcome to episode 4 of the Clinker Factor, a podcast from WCA which looks at the cement industry's response to climate change around the world. I'm Ian Riley, CEO of WCA and your host on the Clinker Factor. In the second episode, I talked to Thomas Schulz, the CEO of FL Schmidt, and Thomas emphasized the importance of technology in addressing climate change. And today we'd like to take a slightly different perspective and look at the development of technology over time. So today I'm talking to Matthias Mersman, who's the CTO of KHD and someone with long experience of cement industry technology. We'll look at the role that technology improvements have already made to the industry's environmental footprint and examine the outlook for further improvements. So this is going to take more than one podcast, but we're going to start today with preheater and pre-calciner technology. And then in future episodes, we'll look at grinding technology, alternative fuels and emission reduction, and then the plant of the future. So Matthias, welcome. Can I ask you to start by giving us a brief introduction to your background and how you came to work in the cement industry?
Yes, of course you can, Ian. Thanks for having me on the program. My background is that of a process and mechanical engineer. And I happened to graduate from the same university as Thomas Schulz, by the way. To be very honest, my way into the cement industry wasn't clear right from the beginning. Actually, while I was doing my studies, I didn't even think about the cement industry. I guess that is part of the characteristic of the cement industry. No, not really many people have them on their radar. So anyway, I never regretted entering into the cement industry over 25 years ago, because I still believe that the cement industry is a perfect place for an engineer to be, because it carries so much variety and width of technological aspects. And I do not regret a single day of having been in the cement industry. So today I'm Chief Technical Officer at KHD, being responsible for the technological lineup, the products. And one of my most pressing objectives is, of course, to line up our product portfolio for the future requirements of the cement industry.
Okay, thanks. So today we're going to talk about preheater and pre-calciner technology. But perhaps before we start on that, you could give us some context. What did a cement plant look like before we had preheater towers? It's kind of hard to imagine one without one.
Yes, that's true. That's true. So first, we got to give credit to some English guys who invented the process of manufacturing Portland cement clinker in rotary kilns about maybe 150 years ago. That was a good invention, and there's a lot of process going on inside that rotary kiln. If you feed a mixture of limestone, mainly limestone, into one end, and then you have a burner at the other end of that rotary drum, as the material passes through that drum, it undergoes a sequence of physical, chemical, and mineralogical processes to drive out water, to drive out CO2, and then finally to form the clinker minerals, which we know as Portland cement clinker. Now, that was a good invention, and it was very energy intense. The energy required for producing a kilogram of that Portland cement clinker may have been around, say, 8,000 kilojoule per kilogram clinker. And people started looking at ways to reduce that energy consumption. And process engineers found out that this is all depending on the efficiency of the heat transfer into the material. And the heat transfer, of course, is efficient if the particles have a good accessibility to the heat. And you can imagine running all these processes in a rotary kiln doesn't give much surface for the heat to act on the particles. So people had the idea in the 1950s to take out some portion of the process from the rotary kiln and do that in a suspension flow. So to suspend this powder into a hot gas, which is actually then the off gas of the kiln, to transfer the heat more effectively into these particles. And that reduces the energy consumption.
So this was, I think, a development that stemmed from KHD. Is that correct?
Oh, that is very correct, Ian. KHD has the pride of being the inventor of the cyclone suspension preheater back in 1950 or 1952. That is true. And we still take pride in being in this position. Now, the interesting thing is what is done for preheating, that is for taking out the water, drying and preheating the material, can also be spun forward for taking out the CO2, which is the process we call calcination. That is happening at a higher level of temperature and also used to be done in long dry kilns. So the first attempts were to take out the preheating action into cyclone preheaters and still have the calcination in the kiln. Now, again, KHD and some fellow engineers in Japan in the early 60s last century came to the idea to even take out this calcination action from the rotary kiln and do that in a device that was then called pre-calciner. And modern plants still operate like this because pre-calcination and preheating is best done in a suspension flow where the heat of the gas can be very effectively transferred into the particles. That is increasing the heat consumption massively, the efficiency of the heat consumption massively.
Yeah, so the early plants had considerably worse energy efficiency than the modern plants. So can you take us through some of the developments both to the preheating and to the pre-calcine?
Yeah, if we assume the heat consumption of a long kiln, and I'm talking about a dry kiln maybe only, the heat consumption in such a setup would be something like 7,000 kilojoule per kilogram or 6,000 kilojoule per kilogram, depending a little bit on specifics, site conditions, and whatever. Now, if we take out the preheating into a suspension preheater, this drops down by maybe 1,000 kilojoule per kilogram. And if we take out the calcination into the more efficient pre-calciner, then we get down to those values which we are operating already today. So we are ending up at something like 3,500 at very efficient plants, maybe even 3,200 or something in that range. So we can say that preheater and pre-calciner technology has cut down the heat consumption half.
And so you're talking about how many stages of preheater. When you do the comparison, did we start with 4 and now we've moved to 5 or now it's 6 indeed?
Yeah, that's also part of the technological development. I guess the first preheaters will probably have been pilot scale with only maybe 1 or 2 cyclones because we had to test whether this really works or not. And very soon it got into, say, a standard 4-stage cyclone preheater. Today, the number of cyclone stages is ruled by the humidity and the moisture of the raw material, because we are designing the exit temperature of the preheater so that it just satisfies the drying energy demand for the raw material. So if we are dealing with dry raw material, we can afford to go with a 6-stage preheater and very low exit temperatures, very high heat efficiency. But it doesn't make sense, to go for a 6-stage preheater and you'll have to afterwards supply additional energy to your raw meal department if you need more energy to dry the raw material. So this is, by the way, a very good example about the very early sense of energy efficiency of the cement industry. The cement process, if you include the pyroline and the raw grinding department, to one energetic unit, the utilization of waste heat is already engineered to the max, and that is something that is really a good example compared to other industries.
So on the preheater, we've seen developments in terms of efficiency and number of stages. And what about on the calciner? What did the early calciners look like, and how have they changed over time?
Yeah, that's a wide subject. I guess until we started discussing about low carbon footprint, the subject of calciner design was maybe the hottest topic in the cement engineering world, because there's such a variety of technological solutions to it and so many aspects to it. The first calciners made in Japan differed quite from the first calciners made by KHD. So in Germany and in Japan were the first attempts, while the Chinese colleagues, their calciners looked more like pots and cyclones. While KHD has always developed calciners like flash tubes. That is a very decisive difference, because the flash tube concept, which consists of a straight tube with almost no variations in diameter, where the meal and the gas flows in the same direction, offers optimum homogeneity of the process parameters. So you have a controlled retention time, you have controlled temperature, exposure. So the calcining process is very much controlled, very heterogeneous. While if you have pot-type calciners, the way the meal moves and the way the gas flows is not necessarily identical. So controlling the process in terms of actively controlling how long does the meal sit in the calciner, how much heat does it get, is quite hard to control.
So I guess for the Japanese and the Chinese to design these pot calciners, there must have been some advantages to that design.
That is true. That is true. That's what I pointed out earlier. There is a lot of aspects to it. Of course, from the mechanical structure, from the space requirement, from packaging that into preheater tower structure, there's a lot of arguments, pro and con. And of course, if you can deal with a calciner volume that is only half, like you can maybe achieve in a pot design, this is in some cases, of course, an advantage. KHD's position on this has always been and still is that we put much stress and biggest effort in optimized process. And we build only flash tube calciners because this is the best way to control the process. And we believe this is creating the highest efficiency. And so we suffer a little bit in CapEx, but we gain in OpEx and in low emissions.
Okay. And recently you've been building calciners that help to control the NOx levels as well. How have these differed from what you had before?
That is also true. Calciners in the late 80s and 90s became a subject of, say, emissions optimization as well. That is because calciners are the piece of equipment that the exit gas from the kiln is fed into. And this exit gas from the kiln contains NOx because of that high temperature flame in the kiln. And the question was how to reduce the NOx emissions. So calciner designs had been adapted and developed in various ways to reduce the NOx emissions from the kiln. And the variety of technical solutions is almost endless, and there are hundreds of different designs for calciners, trying to optimize the NOx reduction, trying to maximize the heat transfer, trying to lately also control the retention time for the burnout of secondary fuels, which is the next requirement that was put to calciner design.
So if you look at the demand for these low NOx systems around the world. Is that something that you see across the board, or is it particular countries that have this requirement at the moment?
Yeah, this is, we understand that to be a natural part of the development of increasing eco sensitivity. It will sooner or later cover the whole world. We hope so. We are actively working on it to help reducing the footprint on the environment. We see that low NOx emission requirement in Europe for a long time already, in Northern America for a long time already. Coming up in India these days, very, very stringent in China. China's NOx emission levels are much lower than everywhere else in the world. And we have just developed a new technology called the pyroredox, which is, you can say, an extension of the calciner upstream, in which we can reduce the NOx emissions coming from the kiln primary without introducing ammonia or other secondary measures down to values which were never to be achieved in earlier days. So we very actively want to contribute to be reducing the ecological footprint of the cement manufacture.
I was in China, working in China for Holcim during the period of time when China brought in the stricter and stricter NOx emissions. And clearly the impetus for that was to try to reduce air pollution in the cities, which have been famously bad. And of course, this same situation we see in New Delhi, we see in big cities across the developing world. So I agree with you that I think it's only a matter of time before other countries see what can be done and require their own cement companies to do that as well.
Yeah, that is so true.
If you look at the way that plants are operated, so I know that in addition to building plants, you also look at helping companies to run them effectively. What do you see as being the main problems or the main deficiencies in the way that cement companies are running this part of their plants, the preheater, pre-calciner, pre-kiln part of the plants?
Yeah, that is very much addressing the issue of secondary fuel, which is a wide field in itself, and which is, by the way, also one of the big levers in all those low carbon future roadmaps. So utilizing secondary fuel is paramount. It is cost effective for the cement producers. It's good for the environment. That is a subject by itself. And utilizing secondary fuels is not always easy. There's a lot of things to look for, starting with preparation of the fuel, handling the fuel, and putting that into the process. Our task in all that field is to design calciners and secondary fuel solutions which allow a most trouble-free operation. We have just launched on the market a new device called PyroRotor, which is a rotating drum attached to the riser duct of the kiln plant, to the calciner, you might say. This machine is so robust that you can put all kinds of secondary fuels with a low amount of pre-processing into it. So that should enable cement producers to increase their secondary fuel firing rate up to 100% of calciner fuel without having to spend much thought and experience much trouble in the sometimes very tricky behavior of lumpy secondary fuel particles in the calciner. There's a whole range of problems that people have learned when using excessive amounts of secondary fuels. It can bring down the plant capacity completely. It can stop the kiln. It can be disastrous. It's very challenging from the process point of view and from the operation point of view. So at the same time, this is the natural way for every cement producer to go in order to reduce his production costs and in order to contribute also to the reduction of CO2 emissions. So we engineers, we have the task to to provide technology that allows easy operatable and maximum substitution of fossil fuels by alternative fuels. And KHD is not alone. All the other suppliers of equipment, they have their products in place, and we will see all along the world. It's starting in China, it's starting in India now. Someday we will even come to America by increasing the use of secondary fuel. It is unstoppable. It will proceed.
Yeah, so we'll cover that in a separate episode with us. I think, as you say, it's a big topic all on its own. And one of the interesting things with alternative fuels, as you mentioned there, is that it depends very much on the local situation, because it depends not only on local industry but also on the regulation of wastes in different countries. And the pyro rotor is quite an interesting development. But anyway, let's save that until later. Just coming back to the preheater and pre-calciner technology, do you see differences in the design philosophy today between the major suppliers, yourselves and other major suppliers?
There is slight, I would say, but first, what needs to be understood is today we're only talking about cyclone preheaters. In former days, there had been other concepts, but we're talking about cyclone preheaters only today. So what is essential to understand is that in some projects and some regions, electrical energy is more expensive than fuel energy. So as these preheaters are producing pressure drop, the target for the pressure drop might be more important in one project than it is in another project. And if you know how your cyclones behave, then you have in your hands to design your cyclone preheater to either optimize pressure drop or to optimize heat transfer and say exit temperature. So it's always a trade-off. It's a trade-off within one cyclone according to its design anyhow. And if you place several cyclones in a row, still you have some engineering degree of freedom. What is important to understand about cyclones is those are machines which are very old. I don't know how many years cyclones are around in several industries. Still, the interaction of flow of gas and meal is very, very tricky, and you can do lots of mistakes. And there are actually cyclone preheaters around which are operated so badly, not because the cement producer operates them badly, but they're designed badly. A little bit of difference in some geometrical parameter can make a whole lot of a change. And what we know in KHD, the efficiency of one cyclone stage is depending on the efficiency of the meal distribution in the meal box, and second step in the collecting efficiency of the cyclone. So you will have to understand that the heat transfer is done better if the meal is distributed better in the gas flow, which means the meal box must distribute and disperse that meal evenly into the gas. So it's a question of designing the right shape, the right flow geometry to achieve best possible splashing. And the same, what you have splashed earlier, you have to collect afterwards in the cyclone. So this comprises a whole lot of process and flow dynamics understanding. And accordingly, the cyclones and the designs of the several suppliers do change and differentiate a little bit. We emphasize very much heat transfer and efficiency. That's why we also have an adjustable splash plate in our meal boxes, which other suppliers don't have, because we know that the position of that splash box at the splash plate plays an important role in the effectivity of the dispersion of the meal in the gas flow.
But are you able to model the gas flow better today than you used to be able to? Is that something that has allowed you to improve efficiencies?
Absolutely, absolutely. The advances in CFD are so massive lately that we can model with a very high accuracy today the exact behavior of the meal in the gas flow, which was not possible, say, 20 years ago. And it's like everything in technological development. There's cooperation between, say, knowledge, software development, hardware development. It all goes together. And definitely today we can rely on much better understanding and much better simulation than our ancestors could do.
So perhaps one way we could tie this together and sort of conclude on the topic is just having a look at the Industry 4.0 and the development of control systems. And with respect to this part of the process, it has improved control, AI, deep learning, etc., had an impact on the preheater precalciner process.
Yeah, definitely. Owing to the fact that 60% of the energy input for a clinker manufacturer is put into the calciner in terms of fuel, it's clear to see that if you run this process optimal, your whole process will be running optimal. And in that sense, controlling the calciner process has always been a focus point of automation. Now, with the new technologies coming up, artificial intelligence, machine learning, and all this is getting a new push. The cement industry, I have to say, was very early also in other technologies like model predictive control and process simulation, very early. So there's no reason to be shy. Working in the cement industry, we have some very good engineers and always had. But now with the new methods we're having, the data-driven methods, we are going to see a new step ahead in the control and automation technology, and that will be necessary in order to fulfill also the stiff requirements we're going to face in the future regarding alternative fuel usage and low CO2 footprint. So everybody's working on it. We are working on it. The cement producers are heavily working on it. This is maybe the hottest potato in the cement industry these days.
Okay, well, thank you, Matthias. Perhaps we would draw today's discussion to a close there, and we can pick this up again next time when we talk about grinding technologies, another area where control systems have played a very important role. So Matthias, thank you very much for joining me today, and I look forward to seeing you again shortly.
Ian, thank you very much. It was my pleasure, and I hope that we reach a lot of people with these important subjects.
Okay, thank you.
Thank you.